So if you only use one zeta, what's called a one zeta calculation, then what you're doing is this. Instead of writing your phi as a linear combination of chi's, more than one function, you just use one of these Slater type orbitals. So that's called a one zeta calculation. Right? So this is your expression for your atomic orbital. And there are some rules that have been developed to get reasonable values for these zetas, these effective nuclear charges, and you can use what are known as Slaters rules. Okay, and in Slaters rules, what you do is you group your orbitals. And the orbital function, the zeta for each of these groups of orbitals, there's a rule, empirical rule that you can use to determine the shielding constant. Okay, so shielding constant is what you subtract from the nuclear charge to get essentially the effective nuclear charge. So, for example, let's say you wanted to know what is Z minus S for a 2p orbit, for an electron in a 2p orbital of fluorine. Okay, so if you want the effective nuclear charge for an electron in a 2p orbital of fluorine, you'd say, all right, fluorine, which group does it belong to? To S and 2p, right? So the shielding constant is 0.35 times the number of electrons in group minus 1. So this is the group for your 2p orbital. This is group minus 1. Right, so how many electrons do you have in the 1s orbital? 2. So 2 times okay, I think I got this one messed up. I got the 6 and the 2 backwards, yeah. No, it should be group minus 1 should be 0.85. Oh, and it should be in the same group. I'm sorry. That should be in the same group. So that's 2 times 6 times 0.35. So there are 7 electrons in this group, right? 2s2, 2p5. There's 7 of them. So there are 6 other electrons that will be shielding that electron. Any electron in that group will be shielded by 6 other electrons within that group. Each of those 6 electrons will contribute 0.35 to the shielding. So 6 times 0.35. And then the one group below it, in this case, it would be this 1s group right here. Each of these electrons would shield it by an amount equal to 0.85. So there's 2 electrons in the 1s. Those 2, each one of those electrons would contribute 0.85 to the shielding. So your shielding constant here for an electron in a 2p orbital of fluorine would be 6 times 0.35 plus 2 times 0.85, or 3.8. So effectively, instead of feeling the force of 9 protons, because of the presence of the other electrons, it will be shielded by an amount equal to 3.8. So it will be feeling the effect of only, as if there's only 5.2 protons pulling it in.